this and I forgot to record it. Okay, so I apologize to you if you expected to have the full thing. I've missed the beginning of this, but we wrote a program. Let me just recap for you. That'll slow things down anyway. We wrote a program here that just has assignment statements. We, modified the mate field, corrected an error, assembled it, and now we're sort of beginning to do the activation record here, where we've identified that before main starts, these lines here, the very beginning, always set EFFF is before main starts. That's sort of the base of the stack here. And R4, though, although it's reserved, is R4 is up here. And R5 and R6 is there. And R5 is somewhere else in here in the stack. So that's R5 and R6 are down in the EFFFs or the high values, and the R4 is global, which is low. Okay, so you have that, and so that gives you a general picture, because R5 and R6 then are going to be set by this. For example, remember R6 minus 2 well, it reserves 2 memory slots. It jumps 2, so it saves. So now, after the first one, R6. Oh, sorry about that. I keep doing this. R6 goes up here. So it's the minus 2 moves it up. This is the slot for the return address. This is the slot for the return value. And so this is like X, E, F, F, E, subtracting 1, X, E, F, F, D, subtracting 1. And then it stores R7 in there, which is here going to be the address of halt, which is X300B, because that's the location in the code where you're going to return. So you're returning close by. Okay, then so that's this first one here. Then you store the return. This stores the 300B. This one here, the R6 minus 1, moves R6 up 1 more. This is the minus 2. This is the minus 1, and we have another. So these are the bookkeeping variables. There's no parameters. So we have the 3 bookkeeping variables for main, the return. Oh, what did I do? Sorry about that. X300B, and this one here is the return value, which doesn't get written yet. Okay, so then R6 now is pointing here. This is the local frame pointer. So what it has to do is it has to set it stores the old local frame pointer. Well, so it's going to store X, E, F, 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 because that's what the before main call, that's what R5 was. Then it's going to move R6. It sets R5. See, it adds to R6 minus 1 and sets it to R5. So it sets R5 to this address. So R5, this one is going to equal X, E, F, F, C, and X, E, F, F, B. So this is going to equal X, E, F, F, B. Now, if there were no local variables, then R6 would equal this, and they would be the same. Yulia, question?
Oh no, I am good, thanks.
Okay,
Sorry.
so this is, well, EFFB, right? We've saved, we know okay, we moved R6 up one. Then, so we're at here, we're at this place here, line 24. And now this line here is the crucial one, because here's the first contact. We make contact with C. We have 5 local variables. Okay, so R6 then is going to go, R6 is pointing here. So it goes 1, 2, well, let me draw some lines in here. 1, I have 1, 2, 3, 4, 5. So R6 is here, so it goes up 1, 2, 3, 4, 5. So our final R6 up here is, again, this is R6. This is the top of stack, also called the stack pointer, because it holds an address. So for this program, it's going to be B, C, B, A, 9, 8, 7, X, E, F, F, 7. Now R5 points here, so R5 crosshatch 0. This is going to be, if I look at my program here, this is going to be the variables A, B, C, D, and some. So if you were just looking at this code and wanted to sort of omit this, I wanted to do this to make it concrete. You can see, because you know what's happening, you can figure out what the addresses are. This is all way down in the stack. This is so the activation record for main is complete now. The activation record for main goes from here to here. For main, okay. So then, if you wanted to, if the main point is to analyze what's the code that corresponds to 1, 2, 3, 4, the 5 assignment statements. Well, since the assignment statements are all writing something to R5, you can separate all this by where it writes to R5, to R5. Oh, no, missed one. Load. R5, and then, no, that's R5. Let's see, load. Oh, there's one there. Okay. So I have 1, 2, 3, 4. Oh, here's one here. R5. And these are all R5 minus, oh, here's one here. R5 minus, oh, but these are minuses, right?
Are we looking for where it writes or where it loads from R5?
Where it writes, and so I've made some mistakes here, right? Because I want store. Oh, here's one. Let's look at all the store. I'm going too quickly. Okay, so look, all the stores for R5. There's a store for R5. There's a store for R5. And it's R5 negatives, right? There's a store for R5, and there's a store for R5, and there's a and here's a +3. This is the one that sets return value from R7. So this one is the one that loads return value. So this stuff here is the return code, is the stuff where you're beginning to tear down the block. So since we're interested in the connections with C, we want to sort of make this program so we can compare what's happening in here, because we know it's happening in order, right? So we have int a equals 15 is gotta be this one here, right? This has got to be int a equals 15 because it's the first C instruction, and we know that this is the way the stuff that is, and you can check now that this R4 plus 2, see, here's R4, here's R4, R4 plus 2. So this is the address. See, there's the 15, right? So it's got the 15, so this is okay. But now the next one here is interesting because it does R4 plus 1. Well, in the code, you have 20, 40, and 60. Down here, you have 120. So this is R4 plus 1, but so the compiler actually does some arithmetic for you because it doesn't want, there's no point in having the LC3 calculate these numbers. It just calculates them on its own. So here, this line is the one that corresponds to int b equals 20 plus 40 plus 60, which equals 120, right? So it looks the same as this because there's only these two numbers. Then this is one that we have. So that's sort of interesting that the compiler does a calculation for you. And so that means the code is uniform for these two assignment statements. Now this one's a little different here for C equals A because it says what's in A gets put into what's in C. So this one loads something from R5, from R5 minus 2, right? Well, let's see. Look at this. The compiler's actually done something suspicious, right? We thought that it was always doing these in order A, B, C, but look, this is 15. So we have to sort of like reorder what these are, right? Oftentimes they are, but when you do when the arithmetic is weird, and I'm not sure, this is a particular compiler issue, that it does something like for this 15, we have R5, 1, 2. So this is A here, right? And this one is B. So we have B down here. So it has something to do with the fact that because it added these up, it chose to put B first. And it didn't care what, so it actually is real. So it's doing this in the same order, but it's storing them in slightly different order. Okay, the next one here is storing it at -1. And it is getting A, which is what you want here, and writing it to C, right? So, but C is -1, so C is here. So this is doing int C equals A. This first one loads the value that's in the variable A, which is R5 minus 2 into R7, then it stores it into R5 minus 1, which is C. Okay, and we have this instruction here. So this next bit here has to be int D equals C plus B. This is like, let's see how this one does. Well, it loads what's in R5 minus 1. R5 minus 1 is C, so it's loaded what's in C. Then it loads what's in R5 minus crosshatch 0, which is B. So it's loaded C and B, then it adds what's in R7 and R3 and puts it in R7. So now R7 holds the sum, and then it stores it in R5 minus 3, 1, let me see, R5, 1, minus 2, minus 3. This one is D up here, right? So we've got, so this one, it does something simple to do, but you see the C lines here are only a few lines. Okay, so what's the last one? Now, sum. There's only one left. Sum has to be the top here, hopefully. And it is minus 3, minus 1, minus 2, minus, you see, minus 1, minus 2, minus 3, minus 4. So it is not quite doing, so let's see. So maybe there's something else going on here. We have in sum, because we have B plus C plus D. So it loads, this one says R7 equals what's in B, right? And this one does R3 equals R5 minus 1, which is C. And so it's adding it from the left, right, B plus C. And then this one, well, what it first does is it adds R7 and R3. So R7 equals B plus C. Oh, that's the point, is that the reason I did this incorrectly. I did another weird store one here. Okay, so then this line loads, which is in R5 minus 3, 1, 2, 3. That does R7 equals D. So we have that. Then it adds them in order. It adds R7 equals R7 plus 3, which is B plus C plus D. And then finally it stores into R4 minus 4, which is sum. So sum is up here at the top. And this is sum gets the value, which is an R7, which equals B plus C plus D. Okay, so you can, so it's going to do these in order, but you can see that you can't necessarily make assumptions. There's 5 local variables, but it rearranges them a little bit for whatever reasons, I'm not sure, for whatever reasons it's doing that. It may have something to do with, let me see, the coming back sum and D, and then it rearranges A, B, and C. It does B first, then C, and then A. So it's not clear. It looks like if I just moved A down here, that would put it back in order. So somehow it's done B, which is this one first. But then who knows? You'd have to look at the C. So the order is not particular. The order depends on the program, right? Depends on the compiler. So you can't assume that things are certain, like you can't, it would be nice if we could assume. So sometimes on a test question, I'll say, assume the variables are in like alphabetical order, like A, B, C, D, and in the real program, they might not be. Okay, well, that's it. Then the rest of the program is tearing down the activation record and then returning. And when it returns here, it's going to get the R7 that was saved here and go to 300B and halt. So what the point here is that each of these instructions bears a certain, it gives you a flavor for how the assembly code is working for these instructions, and that for simple ones, you might be able to predict what's going on, okay? But for complicated ones, might not be the case. So there's a number of, oh yes, sometimes people are, I think the programs that are on RigX do allow you to enter assembly language instructions. So I think some people were a little confused by that. So let me just point out what you do in some of these. Okay, so here's this hello.c program, but here's the one exercise.c, which was on page 144, but I corrected this. It's on page 164 of section 2 of chapter 7. And who knows, that may change, next week when I revise the text. So it's into LC3 assembly language. So the question is, what 3 assembly language instructions correspond to instruction C? Well, you're going to go and compile the program and then look at the assembly code and do what I just did and find the lines of assembly code that correspond to this. And then what you're going to put in here are exactly the assembly, like something like this. Now you see here, a lot of these instructions have crosshatches because you're doing immediate 5 here. These ones are LDR and STR that have it's also loading it with an offset. So that's what this is referring to here when I say enter the, I changed it, made the instructions a little bit clearer. Enter the assembly instruction as it would appear in the program and specify any numerical values in the instructions with hexadecimal numbers. For example, use X, but don't put any extra zeros. So use X1, not X0001. Extra spaces or no spaces between assembly code tokens will not invalidate an answer. And I'm pretty sure that it doesn't depend on case, because what's evaluating these are small Python programs. So the Python programs then will basically what they're doing, so you understand what the task is, they're looking for something like this. So it divides, say, a line like this up, puts it all lowercase or uppercase or something, and divides it on spaces and commas. And it may well change every comma to a space, and then divide this up into tokens and do the same thing with what you type and compare those tokens. So you want the tokens to be the same. And then it also does something where you don't need necessarily to use R7. It checks that whatever, if this was the answer, it checks that whatever registers here is also being used here and here, or is at least being used here, and whatever register R7 here is used here. So as long as it makes sense, you can oftentimes change, like you could put in here, say register 3333, and it would still work. Okay. So I've made the programs fairly robust. And okay, Will, you have a question?
I was just looking through the textbook and I found exercise C on page 156, but then I looked down at page 164 and saw it there as well. So it answered my question.
Oh, okay. So let's see. This is in revision 7. You have to check the revision too.
I'm on revision 7.
So here is, I think, what is it? There's exercise 0.
Yep. It is on 164, but there's also one on 156, which is the same program.
At 156. Now, are these the same program?
Yeah.
Okay, good. That would be a problem if you had. Okay. Okay, so this is being used here, right, as an example of compiling it, because this is one thing that we were doing, which we see here. We have exercise.c, right? And so what I'm using it on this first one is to show you what real Intel assembly language looks like. MASM is there's two different formats. There's the Intel one, which is sensible, and there's the old AT&T one, which is horrible. Science.c-o exercise. So this is it. Here's your source code. Here's the output files we named exercise. It specifies the format because we're saving temporary files. You do this, and then you do ls exercise star or dot star, and you've got a whole bunch of things here. This is the one that was produced by the LC3, but these three .o, .s, and .i are produced by the S is the assembly one. So if you want to look at the assembly, you would open, I think, S here. And this is what real assembly language looks like. Now you notice that there's like file is like there's many more pseudo, they're like pseudo direct, they're like pseudo operations. But you're familiar with these as .n, .org, and then it gives, like, for example, there's a text section, global, there's other, then here's main, right? And then it has some other sections that aren't exactly relevant. So let's see if we can see anything. Well, you can see push, there's some stack going on, right? And these are register names, RPB and RPB and RSP and EAX. So there's the 84 that's in the thing, and then pop, and then return, and you have lots of other pseudo directives. But if you ignore the pseudo directives, this is memory allocation here. If you ignore the pseudo directives, you just look like you're pushing something onto the stack. You're moving it from RPB to RSP. Then you're doing something with this thing here. And somewhere you have, let me see, what is, it's hard, there's lots of extra junk here, right? And then what is the exercise.c program that we're just compiling? Okay, so we see the number 84 somewhere in here explicitly. I saw that a while back somewhere. Oh, there it is. It's explicitly in the program. So this one moves, EAX is the register, is like is the register that holds the return value. And then RET is a thing that's going to move it's going to move, it's going to, anyways, it's the what it stops main. But anyway, so we have this return, we've got the 84 there. But what about the 24, 26, and 11? Well, there's the 61, right? Now, this other stuff has to do with a fancier address. It's doing something different with the registers, but it's because it has a move instruction that's more flexible than our load and store. It can move it between two registers, and it can move it between memory and registers. Anyway, so there's some similarities, but you can see this is like much more complicated to understand, where there's a lot of extra junk. But you can sort of see that, and if you do something with different assembly programs, that you'll see more of the, like you can see LEA, you can see other add. If we actually added two variables, anyway, the point is you can see that what you're learning here is a simplified form of actual assembly language. Yulia, you have a question? We're overtime.
Oh, I am sorry. Yeah, I just couldn't got. May demonstration schedule can be Monday as we don't have a class.
Excuse me?
What did you hear for the demonstration 3?
Oh, there's going to be demonstration 3 this afternoon.
And is the due is Monday?
It's due on Monday midnight. But
Okay.
I know you have troubles with weekend times. Do you think there'll be time for you to,
Monday works perfect. Yeah.
if I could move the due time to Tuesday morning,
It would be perfect. Yeah.
that would be useful.
Yes.
Okay, well, I'll move the due time to Monday at say sometime like 11 or 12 or something like that.
Do you mean
PM.
Tuesday?
Oh,
I mean on Tuesday. In other words, the demonstration 3 will be due next Tuesday at 12 noon.
okay. Thank you
I have
so
to,
much.
right now it's showing at 12 midnight, but I'll change that in a moment to 12 noon on Tuesday. So you can work the problem, you can do the demonstration on Tuesday morning as well as during the weekend. Okay, well, I should probably let you guys go. Have my next class. Chat. Contact with aliens. Oh, I should stop. Let's see.